And we need to do those in parallel so that by 2024, all the technologies, all the capabilities will be available and ready to fly astronauts to the surface of the moon.
EDL, entry, descent, and landing, has always been an integral part, I mean, an important part of discovering another world or learning more about other worlds. Is that just as important as laying on the lunar surface? Because it really doesn't have an atmosphere compared to the Martian surface?
Well, the Martian surface is actually harder to get to because it does have an atmosphere, right. But we are using the moon as a proving ground, essentially. The Doppler LiDAR, the precision landing technologies that we need to get astronauts to the surface of Mars, which is the end game. We want to demonstrate on the moon and then understand how they perform and what we need to do to extend those to the Mars surface.
And so that means, for example, when this technology matures as it's actually deployed, it'll probably fly on missions prior to that, and we'll see test data and verify all that functionality even ahead of the astronauts arriving.
Absolutely. There are things we can do with Doppler LiDAR on the ground here on Earth to develop it and prove its capabilities, and we are doing that as we speak. We can do it on the ground or with aircraft or suborbital launch vehicles. We're going to fly the Doppler LiDAR on a Blue Origin New Shepard next year, and then we're going to take the Doppler LiDAR on 2 small robotic landers and demonstrate it at the moon in a fully autonomous sense before we put it on the system that's going to carry the astronauts down to the surface.
I understand there's a project called SPLICE, and that's where you have the hazard avoidance, the navigation Doppler LiDAR, and all the sensors that are part of this program?
Right. SPLICE has a number of different precision landing technologies, including terrain relative navigation, which we actually use on Earth here, but you use cameras to define waypoints and understand visually where you are. We don't have a GPS network at the moon, so we need other ways of navigating down to the surface. We've got a hazard detection capability, so when you get close to the surface, you want to be able to look and see where the rocks and slopes and even craters are and avoid those. You may remember Neil Armstrong and Apollo 11. He was literally within about 30 seconds of running out of fuel because they flew over a big crater and he didn't want to set the lander down in the crater. So we want to do that. We want to be able to do that autonomously with the hazard avoidance technologies, and then obviously the Doppler LiDAR. And the Doppler LiDAR is really about precision guidance, velocimetry, and position. So with radar systems, we get position, and you have to derive the velocity and rates of the spacecraft. But the Doppler LiDAR gives us a much more precise laser-based capability to pinpoint the landing site and understand your velocity and rates and your position as you get near the surface. And I'll tell you, the beauty of the NDL technology is it has tremendous potential for Earth applications as well. So we're developing it for this very specific spacecraft, human landing system, but it has applications here on Earth, potentially to drive autonomous cars with aircraft, marine applications. It has a really broad-based spin-off capability that people are looking at very seriously.
Now, I know that doesn't drive what we do, but that's got to be really a good feeling, especially on the engineering and science standpoint, to make these breakthroughs meet your objectives, but then at the same time actually open up opportunity for a whole host of different applications.
And that's actually always been part of NASA's mission, not necessarily explicitly, but if you look at all the spin-off technologies that we've developed that we use here in our daily lives at Earth, it's a tremendous investment. And this is probably one more in that long list of things that you'll see in the, in our daily lives.
Well, speaking of NDL, you had a chance to learn more about it.
Absolutely. I had a chance to sit down with Farzin, the principal investigator for navigation Doppler LiDAR, and talk to him about the specifics of how it works. Farzin, navigation Doppler LiDAR. When I hear the word Doppler, I think of like weather radar. How is that different for navigation Doppler LiDAR?
Well, it actually uses the same principles that are used in weather radars. They call them Doppler, right? Because it uses Doppler effect. And the Doppler effect is essentially when an object is moving, it causes a shift in the frequency or change in the frequency of the radiation. In our case, we have a laser radiation. And on the vehicle, when we're traveling, we are shining the laser beam to the ground. And as we are moving, it causes a Doppler shift. And from that, we can get the velocity of the vehicle. This sensor also uses the same laser beam to get the position or the distance to the ground. And by transmitting multiple beams. In our case, we do 3 beams. We can actually figure out what the direction the vehicle is traveling.
But of course, in this case, you're using LiDAR. So
Yeah.
how does the NDL actually work?
Okay, the NDL in general provides position, speed, and direction of motion. These are the parameters you need for navigating. You use that when you drive your car, right? You use your GPS and your speedometer in the car. So it's the same type of things. Now, of course, when we go to other planets or we go to the moon, there are no GPS. So we have to have an onboard sensor to give us position and velocity information. And that's what this system does.
I understand that most of the time we do this using radar, but this offers some advantages.
That's true. You mentioned weather radars. The radars are also used on vehicles, space vehicles in particular, to measure the same type of parameters, position, velocity, your speed, and direction you are traveling. However, laser provides significant advantage over radar. Being a much higher frequency means that it's more precise. The radar diverges, and the laser beams are pencil beams. That mitigates a lot of issues that inherent with radar system. So it's both precision and data quality that this provides.
And this makes a lot of sense with spacecraft because, as you said, we're going to be going to other moons, planets, types of surfaces that we're not already very familiar with. Was that part of the thinking when you started developing this technology?
Well, when we started, actually, the reason was that when we were talking to the engineers who are building these vehicles to go to Mars and other places, we hear a lot of complaints about the performance of the radars. So that triggers for us to start looking at alternatives, and using laser was the obvious choice. So that's how we got started. And so throughout this development, of course, we are working with those engineers in order to come up with the best optimum design that we could. And that's kind of the process that we went through.
When it comes to the moon and perhaps Mars, do you have to do anything different with the system to handle different atmospheres or anything? Or is this a one-size-fits-all kind of system?
Well, as we are developing these for space, we try to envelope all the applications so we don't have to make design changes from going from Moon to Mars. So we try to design it such that the same sensor system that can be used for both application or other places in the solar system.
So as we prepare with Artemis to go to the moon, where are you guys in the development timeline? I mean, do you have a working model? What's the status?
Yes, we are working on a working model right now. It's almost done. So the first engineering units are going to be demonstrated on 2 commercial landing missions in 2021. So throughout this, we are going to be keep improving it, making it more robust. So for the Artemis, we'll be hold out more reliable to ensure that the mission is successful.
And that's really interesting too, because by flying on these commercial missions, you're actually getting flight performance and actual real data to help iterate the system.
Absolutely. This is quite a luxury for us because normally when NASA develops systems, they go through a bunch of tests, in the laboratories, doing vibrations, they put them in the vacuum, they run them over different temperature, they radiate them. You go through all of those and you still have a little bit of a discomfort when you go to the space. Having this demonstration is extremely helpful to us as a developer, and it's also helpful to the engineers that they will have more confidence in these sensors. They will have all this data, they know exactly how it's going to perform. So it's a quite valuable experiment.
And joining us back now in the studio is Franklin Fitzgerald. And Franklin, you actually had a chance to spend time with Farzin and the team over the past several months shooting B-roll and covering a lot of the tests. Tell us about that experience.
Yeah, Chris, several months ago, we got a call and they started talking about, hey, we're going to be putting this together. And we actually went over to the laboratory where they were assembling the NDL, the box that we keep talking about, the small suitcase box.
That's the engineering unit that they're building right now.
Absolutely. And after it was assembled, they said, hey, we're going to be putting together several more boxes. But the one that they completed, they started to do testing on it, like vacuum testing and thermal testing. And I documented that at some of the laboratories here at Langley. But the third test that they called me for was the test that they did at the Langley Air Force Base, where they used the lasers that we have here, models on our table, to shoot a target down the runway in the back of an open cargo van. Yeah, I know.
They improvise, right?
They improvise. But the van was so far away, I couldn't even see the cargo van with my naked eye, but when I looked through my telephoto lens of my camera, you could see it, and you could see what they call atmospheric turbulence, or what looks like heat coming off the surface.
Like a mirage.
Exactly. And Farzine told me that as the lander approaches the surface, you have atmospheric turbulence, but the lasers can work through that to get an accurate location and land like it's supposed to.
And with all these tests, Franklin, I mean, you guys would call them up and they seem to be working constantly on this project.
It felt like it was around the clock. And in one test in particular, the vacuum test, I called Farzine. I say, Farzine, are you going to be available at 10 o'clock this morning? He said, I'll be available at 10 o'clock this morning, 10 o'clock tonight. You can come at 3 o'clock in the morning. We're going to be doing a round-the-clock test for the next couple of days in the vacuum chamber. So there were technicians working around the clock.
We know it's important because this NDL unit is going to be going on 2 CLPS landers, in a year or so. So they have to be ready. So they have to be working around the clock to get it ready.
Around the clock.
And I think that's interesting too, because a lot of times we hear about the technology, we see it demonstrated, and you forget about the actual hours that it takes by not just 1 and 2 people, but a whole team to get this testing done so it's ready to fly.
They haven't been working on NDL just for a couple of years. This has been a long process. I mean, they've been going back to from the pre-2008 working on this. And I had a chance to sit down with Glenn Hines, who is the chief engineer for NDL, and he talked about that history. Hey, Glenn, thank you for being on the show today to talk about NDL. We've been trying to get you on the show for the past 13 plus years. Glad to have you.
Well, thank you so much for having me.
You know, Farzine did a great job talking about NDL. What I want to do is kind of look at the timeline. Let's take us back to the beginning. And to do that, I got a little cheat sheet here. Of course, I have to have on my little board here. Starting back, in 2008, when you started this project, tell us
Yeah.
how did it get started?
So actually, the project started a little bit before 2008.
Okay.
Farzine's ideas and vision of this particular instrument. But our first helicopter flight of it was in 2008. That was out in the desert. We worked that project with JPL. It was a huge system at the time. It was, like, say, the size of a refrigerator.
Okay.
And then we eventually flew it on the Erickson Sky Crane in 2010.
That's huge. That's a big box.
Yeah, and it was a very difficult environment to fly in. There was a lot of vibration on the Erickson Sky Crane. And it was still big. It was around 60 kilograms at the time, the size of about a half refrigerator.
Okay.
But then we started miniaturizing it. We built this, what we call our Gen 2 system, and dropped the weight down from 60 kilograms down to about 28 kilograms and made it the size of a rack mount unit.
Okay.
We flew that on some helicopter tests and did some successful flights. And then eventually we flew that same box on the Morpheus vehicle in 2014.
Okay.
And we flew that at the Kennedy Space Flight Center. And it was working in closed loop at the time with the other systems on board. What that means is the vehicle took off by itself autonomously, picked out a safe spot to land, and found that, and then autonomously flew down to a hazard field that we had built down at the end of the runway, and the vehicle landed there all by itself.
So this was the first test of the system.
Yes.
In a sort of a simulated lunar landing environment.
Exactly. This was a progression of moving the instrument from being huge to being small enough to be able to fly to support these landing systems. And these tests proved out not only its capability, but it proved that we could also do the engineering to make it small enough to fit on vehicles. And we made it one more incremental step after the Morpheus flight.
Okay.
We made it into the size of a toaster. Effectively, that's what we called our Gen 3 unit. And we flew that on the Maston vehicle back in 2017. And that's leading us up to what we're building now, what we call the engineering test unit. We're going to make it robust and resilient enough to work in space.
So what would you say, if you take us back to 2008 and beyond, what was probably the biggest engineering challenge that you had to face during that time?
The biggest engineering challenge was the size of the box, getting it small. And the forcing function for that was the computing system. There's a lot of high-speed computing that goes inside the box to make this thing work. You've got lasers, you've got optics, you've got other components in there, but you need to get all the data processed in real time to get your answers out in real time so that the vehicle can react to it, can use the instrument data to fly. That normally takes a lot of computing power, and we were able to put that onto a board we built here at Langley, to fit inside the box and enable it to shrink. That is pretty much defining the footprint of the box now. So from an engineering perspective, that's probably been our biggest challenge. There are other subsystems in there that we've put a lot of time and effort into making them better, but that's the biggest one from a size perspective.
You know, NASA, as an agency, we develop a lot of cool technology that we use in space, but then a lot of that technology can be used back here on Earth. How could NDL be possibly used in terrestrial applications?
Oh, that's an excellent question. There are a lot of different ways that it has usage right back here. One of them is for autonomous cars. You know, you see that as a up-and-coming emerging technology. A small version of NDL can be used to track the speed of vehicles very precisely. In theory, you can also track objects around the vehicle also, so you can use it to some degree for hazard avoidance for the vehicle there too. But giving it a very precise vehicle speed is of utmost importance to any autonomous vehicle. It needs to know precisely how fast it's going.
Let's kind of fast forward to next year. Where are you going to be when your NDL system is the descent stage of those two landers, and they're about to land on the lunar surface, and NDL starts working, and it's working beautifully?
The state we'll be in is a state of happiness. That's the state we'll be in. We will be extremely excited, extremely elated that this has worked successfully.
Well, Glenn, thank you so much for taking the time out today to kind of give us the brief history of NDL and the technology. I'm hoping, you know, I know you're gonna do a spot landing on the moon.
Yep.
And I know you're gonna do one on Mars one day.
Yep.
But what I want to see is I want to be able to drive in a car autonomously without driving, knowing that Glenn and Farzine and the team have an instrument on board that's getting me from A to B.
Yeah, excellent. I hope to see that day soon. All right.
Thank you, sir.
You so much, Chris.
Thank you.
I'm very excited about the NDL technology for sure, but this autonomous driving stuff is awesome. And if these guys don't deliver, I'm going to call them personally, see if they'll set up a carpool with me, because I'm ready to avoid the traffic situation, get some productivity on the road.
Hey, you know, one of the bigger challenges that they're dealing with is getting it down from that suitcase-sized box to even smaller to work inside of vehicles. The technology has already been transferred, and they're working on it actually close to here at Langley where we were.
Oh, don't forget, Walt said at the beginning of the show, he talked about splice, because remember, NDL is part of a bigger suite of instruments. So you imagine not only having NDL, but then you have the terrain relative navigation built in, and then you have the hazard avoidance and detection. One day you're going to be driving and you get some type of obstacle in front of you, it's going to drive around it, and you don't have to worry about touching the steering wheel.
Perfect.
Let it go on its own.
And you know, it's interesting because that size reduction, they're talking about getting the basic box down to the size of a can of soda. So just think of, there's the lander for Artemis and things like that, but how many other landers that are going to be involved in space exploration that can use that same technology?
Now, we do have some of that same technology in our cars today. We have the side view, the lights that let you know that people are next to you. But that's using cameras. But this is more precise. This is better technology, and hopefully that will be incorporated in other things besides cars and jets and things
Absolutely, like that. Absolutely. Now, Chris, what do you think about the long-term prospects? We've seen a technology like this, and it's being developed and deployed. What's the future look like using this technology?
Yeah, I can't wait till we have those 2 CLIPS missions where the NDL will be flying on the landers. Hopefully we'll get successful data, and eventually if we send humans in 2024, they'll be on the human landers. And then eventually as we get on to Mars, this will be a staple for all the technology and all the landers that will be sent out.
So right now we're doing a show on technology that'll be part of that first return to the moon that we'll have in 2024, and then eventually landing on Mars.
Where are you guys going to be in 2024?
You know what? I'll probably be at the Kennedy Space Center. doing some programming, doing some live shows with you and you probably. And
Hopefully.
hopefully, yeah.
That's right.
Yeah. And I think we're just going to get those goosebumps that we had for the many milestones that we've witnessed over the years here at NASA. You know, I was alive when man stepped on the moon, but I was very, very young. So I didn't remember it like I remember the shuttle mission. So this is going to be very interesting, and I'm looking forward to
You know
it.
the difference is going to be?
It's a
For 2024, he'll have his AARP card.
You know what? That is absolutely right.
But you know, look, it won't matter. What's really interesting is all this technology that we see in development now is going to be riding on the lander, on our part of Artemis,
That's right.
taking the first major step in this process, and we're all going to get to witness it. That is one of the most exciting things that I can think of in terms of NASA in a long, long time, and I'm excited about it, so I really don't care where I'll be.
And knowing this technology right here is a part of Artemis. So,
Artemis. Artemis of Artemis.
Artemis of Artemis.
you're watching NASA Edge.
An inside and outside look.
At all things NASA.
A record-tying spacewalk to upgrade the space station. The station crew receives a new shipment of supplies. And looking forward to seeing Ingenuity take flight on Mars. A few of the stories to tell you about this week at NASA. On July 21st, NASA astronauts Bob Behnken and Chris Cassidy conducted a nearly 5.5-hour spacewalk outside the International Space Station. They upgraded station systems and prepared the outpost for future equipment to deploy experiments into space. Behnken and Cassidy have joined Michael Lopez Alegria and Peggy Whitson as the only other U.S. astronauts to complete 10 spacewalks. On July 23rd, an uncrewed Russian Progress supply spacecraft launched to the station from the Baikonur Cosmodrome in Kazakhstan. Several hours later, it arrived with almost 3 tons of food, fuel, and supplies for the crew. Our Mars 2020 mission is targeted for launch July 30th from Cape Canaveral Air Force Station in Florida. The mission will carry the Mars 2020 Perseverance rover to the Red Planet and the Ingenuity Mars helicopter. This technology demonstration, which has completed its series of testing on Earth, will make history's first attempt at powered flight on another planet the very next time it spreads its wings.
Really, our job isn't done until we see the same test flight being performed at Mars. So next time we fly, it'll be at Mars. But that's our ultimate goal. That's when we'll go, yes.
You can learn more about Ingenuity at go.nasa.gov/Mars helicopter.
This is emblematic of the greatness that comes from these kind of exploration initiatives.
Administrator Jim Bridenstine and other NASA leaders joined a July 20th virtual discussion with the Space Foundation. The event highlighted how NASA's Artemis program for the Moon and our Mars Perseverance rover mission are helping us prepare for human exploration of Mars. Technology development has already begun to enable a crewed Mars mission as early as the 2030s. Capabilities being worked on range from powerful propulsion systems to next-generation high-tech spacesuits to pressurized rovers astronauts can live and work in for weeks. Check out go.nasa.gov/Mars Tech for more about these and other space technologies NASA is working on to make Mars science fiction a reality. NASA's Planetary Protection Office tries to ensure that missions to Mars and other places in the solar system that might have life do not carry too many spores, cells that could reactivate and transport earthly bacteria. This is especially important for a mission such as Mars 2020 that will collect samples for possible return to Earth. The latest episode of our Gravity Assist podcast at go.nasa.gov/planetprotect has more about planetary protection, including what your hand sanitizer has in common with NASA's clean rooms. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
How do you make sense of something you can't see? This is the electromagnetic spectrum, where light travels in waves. Without it, the world you know could not exist. The human eye can only see this very small part of the spectrum, called visible light. But a whole new universe is revealed by looking through the infrared. Infrared light can't be seen, but it can be felt in the form of heat. Every object, whether hot or cold, gives off heat. Special thermal cameras use colors to show us if something is warm or cold. Some objects are hot enough to show visible light, and things that are too cold to be seen by the naked eye can let off an infrared, such as your body or this cup of coffee. IR light can be used in very practical ways. Longer IR waves can cook your dinner. Shorter IR waves that are used in your TV's remote control, and firemen use IR cameras to see through smoke to find people trapped in a fire. So how does this apply to a telescope? On top of showing us colder objects, infrared wavelengths can see through large amounts of gas and dust, lifting the veil to what lies on the other side. Spitzer sees objects like exoplanets or the Milky Way by looking at their infrared glow from the heat they give off. This gives us the ability to see what is beyond. And that's IR in a minute.
If they're going to make something that we don't know how to burn in a rocket engine, let's do some research. My name is Diane Linney, and I am working to build refineries and gas stations on the moon and Mars. One of the first things we need to do is we need to dig up our dirt. I was working my vegetable garden using a small rototiller. The dirt was very dry on top, but of course, as soon as I tilled it up, I got some wet dirt. And I thought, wow, we're trying to harvest the water out of the soil on the moon and Mars to process it into something more useful. We get to play in our sandbox. We can measure how much soil went up into the scoop. Actually, I wanted to be a lawyer when I was in high school. My high school physics and calculus teacher said, you're a woman and you're really good in math and science, you should try engineering. Up until now, we've taken everything we need with us. We're trying to build gas stations and refineries so we don't have to bring all our propellant with us. Our ancestors called it living off the land. It's just a lot of fun that we get to try and push the technology and make new things.
The complexity, the systems that we've brought together in this one place to do something that very few places in the world do, launch humans to a low Earth orbit and, hopefully with a new program into, farther reaches of space. So when you go to a system or a place like that, you can't help but be overwhelmed.
Every space shuttle mission began with a fiery liftoff from Launch Complex 39 at NASA's Kennedy Space Center. The launch complex for the space shuttle had two pads, Pad A and Pad B. If the launch pads demonstrated anything, it's that complex is the right word for the two pad areas that handled the shuttles for about a month before they made their trips into space. Outfitted with everything a spacecraft and its crew would need to take the final leap into space, the pads handle fueling duties and crew support and held precision machinery for a range of payloads. Its graded floors and gray paint, along with armored boxes for instruments, telephones, and elevators, revealed a style more Spartan than space age.
You always find something that you didn't know. And you've got so many systems. You've got system level experts and technicians that have been out there for so many years, dedicated, essentially many of them their entire careers out there. Even though, it's a lot of steel, a lot of wires and lights and tubing and that kind of stuff. It does it interfaces to a flight vehicle, so you have those complex interfaces and there's always something to learn. It may look kind of Spartan, but it's got its hidden treasures.
The launch pad and all its fittings were built to withstand the brute force of a launch, which would rattle the pad with intense fire, corrosive exhaust, and thunderous sound waves.
Tested, let's put it that way. There's a tremendous amount of force that gets placed, the liftoff on the structure, on the mobile launch platform, the MLP, heat, acoustics.
Each pad featured a shallow slope concrete pyramid about 40 feet high with a flame trench carved through the middle to channel exhaust away during launch. Launch pads were first built for the Saturn V rockets of the Apollo program. Back then, the launch complex did not have any permanent service towers because the support structure was on a mobile launch platform and traveled with the rocket to the pad.
The element of the history, to think back and to stand in places where people were launched to the moon, that has a real place for me.
For a shuttle, a pair of support structures called a fixed service structure, or FSS, and a rotating service structure, or RSS, were built at the pad and would remain there for all 30 years of flights. Both structures carried wiring and other infrastructure needed to support and protect the space shuttle for weeks at a time. A shuttle stack, meaning an orbiter attached to an external fuel tank and a pair of solid rocket boosters, would move to the launch pad about a month before liftoff. The shuttle was connected to networks of data cables, water lines, and the fueling system.
Unless you were out there when the workers and technicians and engineers were out there, it's hard to capture the elements of these people working together as a team, doing complex tasks, complex jobs, with a vehicle there that's just loaded with solid propellant. It could be dangerous as heck, it really is. And they did it routinely and made it safe.
There's also a bathroom, complete with stainless steel fixtures instead of brittle porcelain.
And when we do give give some tours up there, groups come up there, I always point out that that's the last toilet on Earth.
Before launch day, the RSS covered most of the shuttle and provided a clean room that safely moved space probes, space station modules, and even NASA's Hubble Space Telescope into the shuttle's cargo bay without contaminating them. Other parts of the launch pad gave workers access to most areas of the shuttle stack, which stood up to 184 feet above the surface of the mobile launcher platform. The launch pad was woven throughout with propellant lines, wiring, and machinery.
There's so many complex things out there that could literally kill you, if you did something wrong, or not just yourself, it could be, devastating. And we do it safely, routinely, day in and day out. That's testament to the workforce and to what this nation built from the Apollo era, learning through hard lessons.
Launch day was also when most of the structures at the pad came to life, mostly by remote control to keep people a safe distance away. The huge white spheres on either side of the shuttle would pump supercold liquid hydrogen and liquid oxygen into the shuttle's external tank. Each propellant had to flow through long lines from the spheres about a half mile from the shuttle.
As you get closer to launch, things just kind of step up, and you can feel it, just pure excitement, really, as you're getting closer.
The last people at the pad on launch day were the astronauts. They headed into the white room, a kind of cramped locker room, before boarding the shuttle. With 2.5 minutes to go, the gaseous oxygen vent arm and its white beanie cap retracted from the top of the external tank, clearing the way for the launch. About 16 seconds before launch, some 300,000 gallons of water poured onto the launch pad. What might seem to be done to protect against the blazing fire, the water was actually for sound suppression to dampen the vibrations produced by 7 million pounds of thrust. Fire and thunder would produce a show unlike any other.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery. A tribute to the dedication, hard work, and pride of America's space shuttle team. The shuttle has cleared the tower.
Some of our team would work late shifts, so you kind of had to go home and sometimes, watch it from the river, just like the other folks would, or something like that, which I actually kind of enjoy. If I couldn't make it into center in time, just kind of being out there with the general general public and everything like that. Just sit back and watch the kids and people enjoy a beautiful launch. You know, it's part of my joy, I guess.
Now that the space shuttle is retired, the pads are being prepared for another transition. The structures that marked the space shuttle era have been removed from Launch Pad 39B, so it can handle several different types of launchers that are expected to make up the next generation of space exploration. Pad 39A, the starting point for some of NASA's most famous flights, including Apollo 11 and the first and last shuttle flights, will look as it did during the shuttle years for the near term, echoing the thundering success of the space shuttle program.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
2 solid rocket motors. That's a pretty rough ride, but you can feel the thrust tail off right before they separate. And, you get an indication PC less than 50, and then, you're going to be there 2 minutes, 5 seconds or so. They separate away. There's a huge flash in the front window, a big bang. You can hear the set motors push those away. And then it's just as smooth as can be on those main engines. They're phenomenal pieces of machinery.
The Space Shuttle main engines have been one of the brightest success stories of the Space Shuttle's 30-year career. Powered by a combination of fuel and oxygen, a single SSME, as the engines are called, produces about 500,000 pounds of thrust. Working with the 2 solid rocket boosters for the first 2 minutes of launch, 3 main engines push a shuttle up to Mach 25 and into orbit in 8.5 minutes.
We call the SSME an extreme machine, and it's extreme because on the inlets you got liquid oxygen and liquid hydrogen, and liquid hydrogen is minus 420 degrees Fahrenheit, so it's extremely cold propellant that we're putting through the turbo machinery, and then we're burning it in the main combustion chamber at 6,000 degrees Fahrenheit. So that's hot enough to melt iron.
It can do that without melting because the engine pumps the cryogenic hydrogen through a series of 1,040 tubes lining the nozzle. The supercold fuel keeps the flames from touching the sides of the nozzle. There also are a pair of turbo pumps that move the propellants through the machinery and into the combustion chamber quickly. The turbo pumps alone produce more power than a locomotive, even though they would fit on a desk. Providing that amount of power safely calls for extensive testing and inspections of each engine and their turbo pumps. A main engine gets examined from the time the shuttle lands until liftoff. Highly trained technicians use long, flexible lenses called borescopes to look at each engine's insides for cracks and other defects.
A skilled technician engineer can perform a real good borescope inspection of bearings, seals, and actually the turbine blades, nozzle vanes, pump blades, and diffusers.
The engine's success did not come easy. Engineers began testing engine designs in 1975 at NASA's Stennis Space Center in Mississippi. Just getting the startup sequence right took months and months of complex work.
Well, of course, the first test of the Space Shuttle main engine on A1 test stand was like 20 milliseconds. I mean, it took a long time to develop the start sequence of the engine, and it was 20 milliseconds at the time, finally 40. They worked their way up to 1.5 seconds, which is a critical time period in the thrust buildup of the start sequence, and then it just went on from there, and it took a long time to actually finally get to mainstay.
The shuttle's main engines made their first flight test on April 12, 1981, along with the rest of the Space Shuttle system. Although the engines had been fired on test stands, no crew flew with them until Commander John Young and pilot Bob Crippen rode them into orbit on STS-1.
And when that whole vehicle got together, we put the crew in and we counted down, and we saw engine ignition and all 3 engines come up. It was just an extremely rewarding experience to see that and see the SRBs fire and that whole orbiter take off and fly. It was hard to describe because of all of the activities that I know led up to that and all the people involved in it to see that as a successful mission, because we didn't have an opportunity to fly it unmanned before we flew it manned. So that's the first time this country really did an experiment with people on board.
and it all worked. Though the shuttle engines are smaller than the mammoth F-1s that powered the Saturn V's first stage, they had to be far more efficient.
And then this was the first time we had to design an engine that would operate for 8.5 minutes. In the Apollo program, the first stage engines operate for about 200 seconds, and it basically gets you up to about 50,000 feet or higher through the heavy atmosphere, and then the first stage is spent, and then the second stage takes over. In this case, the SSME was designed to start on the ground, have the ability to health check it before the solid rocket motors ignited, and then commit to launch, and then stay running all the way through orbital injection velocity. So that made it run for 8.5 minutes. So that was different than engines we had built previously.
Along with the brawn of hundreds of thousands of pounds of thrust, the engines carry very delicate brains that take constant measurements of the systems dozens of times every second.
This is the first engine we built that had an active onboard digital computer. And the computer has a program in it that runs through its full cycle in 20 milliseconds. So 50 times a second, it's out reading valve positions, sensor data, and we have algorithms in there that allow that engine to have what we'll call health monitoring. So we have active flight red lines that in the event that temperature should exceed the limit, that engine will automatically shut itself down to prevent a catastrophic failure.
No mission ever failed because of a space shuttle main engine. Not a couple saw close calls during launch. In 1985, one of the engines on Space Shuttle Challenger picked up a problem.
So they actually shut that engine down at about 18,000 feet per second, let the other two engines run the vehicle until it reached the actual velocity required to make orbit. So it was a successful mission, and it just showed that the redundancy built into the engines really paid off.
The Space Shuttle's main engines also had a requirement no other engine faced before. They had to be reusable.
Reusability created issues with hardware embrittlement. It was hydrogen molecules embedding themselves in the material, causing embrittlement later on. So that created life cycle issues. And we were always talking about what's the remaining life in the hardware.
The SSMEs produce nothing but steam when they fire, another departure from previous rocket engines.
Oxygen, hydrogen, when it combines and creates water, it's very clean. A lot different from the Apollo days when you had liquid oxygen and kerosene. Well, this engine's extremely clean. And people are amazed when they look at the engines in the shop that have flown 10 times or more. They look brand new.
The shuttle main engines have proven to be extremely reliable machines with a record of reusability and success without parallel in rocketry.
But SSME is in a class all by itself. And of course, the reliability that we get out of the SSME is the reliability and the performance that allows the shuttle to fly.
As far as the extreme temperatures, the pressures they operate, the fact that they have been reusable and so reliable from STS-1 to STS-135, I still rate the main engines at the top.
For two of NASA's storied space shuttle orbiters, the lights have gone out for the last time. Discovery and Atlantis were permanently powered down in December 2011 as teams at NASA's Kennedy Space Center in Florida prepare the vehicles for public display. It was an emotional milestone for the technicians, test conductors, and system engineers who have spent years, even decades, preparing each spacecraft for its next flight. The final assignment for Discovery's processing team on December 16, 2011, was to close the 60-foot-long payload bay doors. Many gathered for one last look inside the shuttle's payload bay.
Even at the Smithsonian, there's no plans to open those payload bay doors on Discovery. So as far as we know right now, those doors will never open again.
Then it was time for the spacecraft operators on Discovery's flight deck to shut down the power.
Okay, PRT 1 off now, PRT 2 off now, PRT 3 off now.
Actually, our center director, Bob Cabana, was there. So he actually pulled the plug on that power up sign, and that was it for Discovery.
December 22nd was the last day that work on Atlantis would require power. Its starboard robotic arm and Ku-band antenna were stowed inside the payload bay for the vehicle's upcoming move into temporary storage.
So we were anxious to get as much work done on Atlantis and get to a point where we could then continue to do work on Atlantis in the vehicle assembly building while she was staged there in a waiting mode.
Then the focus turned to the flight deck as Atlantis, known by the shuttle team as OV-104, was powered down for the last time.
AC bus sensor 1 off now. AC bus sensor 2 off now. OV-104 final power down is complete.
Discovery and Atlantis have gone dark, but the team has one more power down to get through. Shuttle Endeavour will be next.
It's sad, but you know, progress, you have to move on. So something has to be done, and I'm extremely proud to be a part of it till the end. Extremely.
Throughout the Space Shuttle program, a familiar launch day sight was the shiny silver vehicle known as the Astrovan. Before each launch, astronauts smiled and waved as they left the crew quarters and boarded the van that would carry them to meet their fully fueled ride to space. The vehicle had wind its way across NASA's Kennedy Space Center in Florida as it carried the crew to the launch pad. It was an exciting ride for the crew members, but especially for the rookies ready for their first trip to space.
The first time, it's just everything about it. It's just, you know, the anticipation, excitement, you know, you're a little bit nervous, but it's, I mean, it's just neat to know that, you know, you're one in the series of a very long line of astronauts that rode in this vehicle going to the pad, you know, for a flight to space. So it's pretty cool.
Early shuttle crews had fewer astronauts, so they rode to the launch pad in an Apollo-era transport van. But since 1984, each shuttle crew traveled those 9 miles aboard the current vehicle. The modified Airstream motorhome only racked up about 27,000 miles in its 27 years of service. That's because it's used solely to transport the astronauts for each mission.
But I always associate this vehicle with flying, because you only get in here twice. You get in here for TCDT, which of course is the launch rehearsal, and then launch day.
The only other time the Astrovan was used was to take the astronaut back to crew quarters after landing. The vehicle's appeal is rooted in its tradition rather than its decor.
It's not really extravagant, kind of like bench seating, and it's pretty crowded on launch day, especially with a crew of 7. You know, I think everyone's trying to cut the tension with a joke or two from time to time.
The interior's narrow center aisle is paralleled by long benches. Lift-out sections accommodate the ventilator units used to circulate cool air through the astronauts' bulky orange launch and entry suits.
This is the only place they have liquid air, and liquid air is really, really good. You know, we have this cooling garment that circulates water cooling, and in the hot Florida sun, it's nice to have it. They plug that liquid air into you, and it just blows this cool air throughout your suit, which is really nice because it actually dries your suit. And the only place we get to have it is in here. And I don't know why. It was like a special treat on launch day.
Now, while each crew no doubt had their own unique take on their ride to the launch pad, Shuttle Atlantis STS-135 mission crew took in the significance of the final ride for the Space Shuttle program.
It was really special this time because there were so many people here. And I think even though it's kind of an anxious time as you head out to the launch pad, because you know this might actually be the day, on this particular day, you know, the last flight, I think we were all really amazed at how many people showed up. I mean, even on the road, you hang the right turn to go to the pad, and the road was lined with people waving American flags. It made me feel good, you know, to know that the shuttle program meant this much to so many people, and not just national, but international. I mean, a lot of people turned out to watch the grand finale, if you would.
While the vehicle won't be taking any more shuttle crews to the launch pad, NASA plans to keep it ready to ferry future astronaut crews to the pad.
I would like to keep this tradition. You know, I don't know if any of us will get to fly on the next vehicle, whatever that vehicle may be, a U.S. vehicle, but it would be kind of neat to have some of it be the same.
You know, and actually traditions are important in a business like this. It keeps everybody connected.
Everybody ready? What happened, Captain? Hold on, everybody.
So after riding the Astrovan to the launch pad a number of times, what would it be like if a space shuttle commander got the keys to take it for a spin? STS-135 Commander Chris Ferguson found out.
There's 0 to 35 in a minute and a half. That was the most white-knuckled event I've had. I pronounce this vehicle fit for another space program.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth. 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
NASA researchers spend weeks, even months at a time, in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation ICEBRIDGE, a multi-year study of polar ice conducted by the NASA Airborne Science Program. ICEBRIDGE sends NASA's P3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like ICEBRIDGE. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for ICEBRIDGE to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once you arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names. We'll do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out and making sure that we can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project. Logistics is huge for something like this because we have to make sure we can all support the people in the field as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions, and they will talk with the airfield, set up and tell them what we're going to be doing. And then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we put them right on the slide there.
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
The DC-8 flight operations team works around the clock to support Operation ICEBRIDGE, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission, the DC-8 is reconfigured for ICEBRIDGE. In 3 weeks' time, the plane is transformed into a working science laboratory with a suite of radar and laser instruments and cameras installed throughout the cabin, cargo pit, and fuselage.
Yeah, the unique thing about the DC-8 is that it was modified to accept, at this point, we've got about 100 different instruments that have been integrated into this airframe. And so part of the modifications that were done early on was to make the airplane as versatile as possible. So if you were to look through the airframe, you'd see cutouts in both the bottom of the aircraft and the upper side of the aircraft. And a number of the windows were modified to carry structural loads of instruments being installed as well. So we can look in pretty much every direction there is outside this airplane as we're traveling through the sky.
Once the science instruments are installed, the flight operations team conducts a series of ground checks and instrument test flights over the California desert to make sure the DC-8 is mission ready.
Looks like maybe it's level now. Right, looks like it's a wings level and rock course.
So the reason why we picked these sites over the desert in California is because they have these dry lake beds there. And they are a very flat area that's ideally suited for our purpose. So we can put a GPS receiver on a car and kind of drive around on these flat lake beds, measure them, and then a few days later fly over the same area with the DC-8 and take a measurement from the air, compare the two measurements, and use the data from the ground to calibrate and validate the airborne measurements.
While the aircraft is prepared for the trip to Chile, the science and flight operations teams are required to undergo specialized safety training, regardless of if they've flown on the DC-8 in the past.
Well, for the DC-8, everybody who flies has to go through basically a safety briefing. We go in a little bit more detail because we do more things on our airplanes than commercial airliners do. From our pilots, they go through survival training, water and land, and depending on where they're going, some of them have been through Arctic. All of our crew members, they all have to go to altitude chamber, water survival, land survival. And what we do here is we just build on that and then try and bring anybody else that hasn't had any formal training up to speed so they have at least a working knowledge of the kind of conditions that can happen if something was to go wrong with the aircraft.
Safety equipment tailored for ICEBRIDGE is also packed on the DC-8.
Overhead compartments, we've got 20-man life rafts. There's 4 of those on board the aircraft. We have 2 what we call global survival kits, which has different survival items inside of there. For this particular deployment, we also have anti-exposure suits, which if they were going to the water, we have enough for everybody on board the aircraft for that.
Once the aircraft and passengers are cleared to fly, it's time to pack up for the long transit flight from Armstrong Flight Research Center in California to the southern tip of Chile. The exhausted team gets an opportunity to rest on the overnight journey to Santiago, where a second flight crew is on standby to complete the journey to Punta Arenas.
To get to this part of the globe, it's about 14 hours of flying. We had pre-deployed a crew to Santiago to join the flight at that point, so that the crew that flew all night could then step out of the cockpit and rest. And that allowed us to continue on that next day down to Punta Arenas, Chile, without having to stop overnight.
It's a cold and windy welcome at the Punta Arenas airport, the mission base for Operation ICEBRIDGE. The scientists and flight crew will call this place home until the end of November.
We are setting up base stations here at the airport that record the GPS data for various instruments. We're talking to people in the weather office, at the tower, the air traffic controllers, and that typically takes about a day, getting everybody settled in here and preparing everything for the first science flight.
With 2 complete flight crews available, science flights are planned on consecutive days to collect as much data as possible over Antarctica.
On a typical Punta Arenas deployment, we have about 300 flight hours, and if we fly as much as we can, which we typically do, we kind of travel a distance in Antarctica that's equivalent to 3 or 4 times around the equator.
I think this is a glacier we're crossing.
Flight tracks are carefully designed by the ICEBRIDGE science team months in advance. Survey lines need to be precise, not only to make repeat measurements in exact locations, but also to ensure the plane keeps a safe distance from specially protected areas and animal habitats. A sophisticated guidance system on the DC-8 helps the flight crew keep the plane on track and navigate around more than 1,700 known wildlife locations on the Antarctic continent.
Some of the flights are hand-flown using moving map displays that have a flight track depicted on them. Others are guided by what's called the ATM instrument, where it actually puts out a signal that we feed into the aircraft navigation system, where it guides the airplane laterally.
So the ATM stands for Airborne Topographic Mapper. We designed a supplemental system to the ATM. Some people call it the ATM Navigator. What it does is it couples into the aircraft's own autopilot and helps it to steer the aircraft as accurate as we need it to be. We can generally steer the airplane well within 100 feet and often within 20 feet of where we want it to be. And that means that if you imagine a line that represents our desired track, more than half the time that line will lie within the cabin of the aircraft.
Antarctica's harsh and often unpredictable weather determines when and where the ICEBRIDGE team will fly each day.
I've got rising terrain, 12 o'clock, 7 miles.
Tally-ho.
Tally-ho, and I'm going to start climbing here.
Pilots need perfect visibility of the terrain for safety.
We'll clear it. It does get steeper as we get closer to it, so we can pitch up a little bit.
Several science instruments need a clear line of sight between the aircraft and the ground to collect proper measurements.
Meteorology is obviously a very big deal with ICEBRIDGE. It essentially governs everything that we do on any given day. We have to fly down low and near the terrain in order for our instruments to work as they're optimally designed to work. So it means we need clear skies below the altitude at which we're operating in order to do this kind of work. We know from experience which parts of Antarctica are likely to have good weather and which parts are not. So we designed the missions so that each of the missions has a maximum chance of success based on the likely weather scenarios.
We come up with about twice as many mission plans as we can possibly fly in the field. And that's simply so that we have enough target areas to choose from that have good weather while we are here in the field. And then we prioritize these plans.
We have to spend a very large amount of our time while we're in the field trying to sort of ascertain what the weather is going to do. It's a bit like reading tea leaves. It's a very inexact science. We depend entirely on what the meteorologists tell us through computer models. We talk a lot to the meteorologists here at the airport. They're terrific. They give us a lot of help.
The Chilean hosts provide everything from weather expertise to daily flight lunches for the ICEBRIDGE team. Airport firefighters and emergency responders are also prepared to help in case anything goes wrong with the aircraft.
So we don't use retread tires.
The DC-8 is not your typical airplane. Structural enhancements, new engines, and cutting-edge data systems make the aircraft a versatile, long-endurance platform for Earth science research.
The DC-8 is uniquely capable for this kind of operation, mainly because of its long legs. It can fly for about 14 hours on a full fuel load.
We have to pretty much commute every day to Antarctica and commute back. And then we need also the capability of collect several hours of data. Typically on every flight we collect several terabytes of data altogether. So we have 8 different science instruments on the aircraft. And in total, it's a very complex set of measurements that we take over ice sheets, and doing it all at the same time in the same location from one airplane. It's really a tremendous resource.
It is amazing that a large airplane that was designed originally to be an airliner could be so diverse, but by its design, it meets a lot of the requirements NASA had set for the type of science studies they wanted to execute using the airplane to support. This particular airplane was built in 1969, but many of the systems have been upgraded over the years to keep up with current technology. For instance, the airplane has a satellite communication system on it, which something like that didn't even exist when it was originally built. So what's nice about that is we can move data real time during the flights off the airplane to people anywhere in the world via the satellite system and then the internet, and they can send us information real time as well. We can X-chat, it's like texting back and forth to each other. We can send photographs, we can send technical data. You don't have to actually be on the flight to participate.
My view of this airplane is that it's the ideal airplane for the kind of mission we use it for, because it's built very strong. And in the old days when these were being designed and built, the airplanes were overbuilt to be on the safe side. We have a nickname for it. It's a DC-8, and the DC stands for Douglas Cable Car, because unlike the modern airplanes that use electronics and hydraulics to control the airplane in flight, this airplane is controlled with steel cables. So we do hurricane research, we fly through hurricanes, and we do a lot of different types of scientific research. And the airplane can take a lot of damage that would cripple other more modern airplanes, and this airplane still flies fine. It's like an old truck. It's solid and almost indestructible.
A wall of stickers at the mission director's console tells the story of the many missions the DC-8 has flown since it went into NASA's service in 1987. This aircraft and many others operated by the NASA Airborne Science Program fly thousands of hours every year all over the world to support a variety of Earth science research missions. It takes careful coordination and detailed planning behind the scenes to make these missions possible and to gain a better understanding of how our planet is changing.
I've always always thought like, oh my gosh, when you go to space, like you don't have to grocery shop for like 6 months.
I think it's going to actually put me on a schedule for eating. I am horrible at eating at all hours of the night. I miss lunch.
We're also talking about like beverages. Like we can probably only drink powdered beverages or water. So nothing, no sodas.
No sodas.
Nothing carbonated.
No.
Yeah. It's just.
I think it'll be a little bit more healthy than what I normally eat. Plus, I get to eat everything with tortillas. And I'm from San Antonio, so. I will say we are doing this over a holiday weekend. You have huge barbecues and lots of great food. So I think I'm going to want to eat some really good ribs and, you know,
like
fajitas. Solemnly swear to eat all of the astronaut food and not cheat.
Never.
Never.
We're in this together. So if we feel weak,
Ever.
we'll text each other. Maybe
We chose 7 days out of the standard menu. You're going to have a protein, some carb, some fruit. The other large category of products that we have are thermostabilized products.
Which is sort of like a military ration that we don't have to refrigerate to keep fresh.
Can't do them in a microwave.
I was going to say, it looks like something that can't go in a microwave. I was going to ask because I didn't want to find that out the hard way.
We also have rehydratable food, which is this type in a vacuum pack where we have to add water, either hot or cold.
We're going to give you a syringe.
Oh, I don't like needles.
And it comes with a needle. So this is
You have to
how
carry
you
that
would
around, too.
rehydrate. Okay.
I don't think we would want to have that laying around our office.
Can I take that through airport security?
Yeah.
It is the day before we start the food challenge, and I just went to go pick up all the materials from our wonderful food lab. So they're all packaged and in my trunk. I asked them what I should eat as my last real meal, and they said something fresh, maybe a salad. The problem is I was thinking nachos, so...
As I suspected, I wouldn't have time to eat in the airport. I'm probably going to grab something to eat on the fly. Hopefully there's some tacos.
So like I said, I was debating healthy or, not healthy. Of course, I chose nachos.
I did end up picking up some tacos, some shrimp tacos actually, with some rice and some beans. Told you I love tacos.
I think it's important to always choose nachos, so I'm going to call this hashtag she chose nachos.
She chose nachos. He chose tacos.
So I have beef and mushrooms, rice pilaf, tomato and artichokes, and a wheat flatbread.
Well, I don't know about that. I have grilled chicken, mac and cheese, vegetarian chili. We're in Texas. Come on. Cran apple dessert.
Oh man, I already remember she told us to tear it so there's no extra pieces of trash.
Oh, so like if we were in space,
So
this
like
would all be floating around.
Yeah. Once we open those packages, the food is what we consider to be liberated, and it can just float anywhere. And sometimes you find yourself using your spoon or your mouth to chase around the food. Make sure you get it all in your mouth instead of stuck against the wall or somebody's face. Let's heat up a bowl of water and set these green ones in there. Yeah. And it looks like it's getting to be the right consistency. Yeah. We might have not done hot enough water too. That might be why it's not absorbing like all the way.
Okay,
Okay, this is good.
This is interesting. It's not bad. Wait a minute. What's this?
This is good. Yeah, the artichokes and tomatoes are good too.
Should I try and eat it like this?
Yeah.
Ooh. You should have just got straws. I could have went.
Right. This is making my day. Like, this is a treat.
I have cran apple dessert.
This would remind me of home.
Yum.
So it's been a long day, but I did not get hungry at all. I had my butterscotch pudding as part one of my snacks. I was wondering if the workouts will be hard. They're pretty much the same. I feel really high energy, and I didn't even have coffee this morning. I'm actually really excited about this chicken, corn, and bean. This potato medley actually looks like some potatoes with spices and melted cheese on it. I'm very excited to get some melted cheese texture up in here. Little butter cookies look really delicious and super bougie.
So you'll see I have some Caribbean chicken, pesto pasta with some corn, tortillas, vanilla pudding, and some pears. I got a little bit better at actually making the space food today, but I punctured the actual corn. I cut through it, so I had to rehydrate it through the side. So lesson learned, this smells absolutely delicious.
It's my boyfriend's last day at his old job, so one of his favorite clients brought him these delicious, huge-looking cupcakes, so none for me.
Woo! Do you see that? This is science, y'all. So
Be a nurse now.
I get. My mom would be proud. Like, Mom, I'm doing nurse things today. Look at this. Oh, okay. This looks like oatmeal. Do PR for NASA, they said. It'd be fun. What are you having for lunch? What's your main?
I have citrus salad, and then my main thing is fiesta chicken.
Ooh, I love fiesta.
Yeah, and rice. yeah, rice with butter. So I'm really excited because I think our food's going to be warmer today.
I agree.
I think we did this right with some practice yesterday.
This is some smoked turkey.
Oh, God.
Leaking. I wasn't expecting.
It's like
it smells funky. Cornbread dressing, and then some cauliflower. I'm not a fan of this.
Today we're eating in the LBJ room. So President LBJ is who Johnson Space Center is named after.
We should do a toast.
We should. Go LBJ. Woo! Oh, mine's closed.
And so here we go. This is really good. This is the chicken noodles. Let's try some of this green bean. Oh, that could use some hot sauce. The lentil soup. Ooh, it's hot. Ooh, hot. See, these are actually my tortillas. Astronauts on board the International Space Station can actually eat tortillas, and it's one of the things that they like to do because you can pretty much grab anything that's floating in space with them.
2 quick miscellaneous notes. I've been living a really scheduled life and waking up early and going to bed early because I've been having to wake up with enough time to make breakfast. And then I go to bed shortly after dinner just so I don't get hungry again.
I think Dan has a burrito.
Oh,
I
yeah.
am jealous right now. I went for peach and queso.
Apples, fresh fruit.
Which may or may not be organic.
My snack was chicken in a pouch. So.
Mine was tuna.
Yeah. There you go.
Lemon curd cake. It's kind of like your rice.
Not your grandma's. I was just at the mall, and whew, that was a week time because all of my friends, I got some really good appetizers, and when you're just all sitting around the table together, I had to really stop myself a couple times to not mindlessly reach for some of their chips or pretzels.
What are you eating?
A cupcake.
And what is Isidro eating? Space chocolate.
Space chocolate.
Yeah.
How do you feel about the astronaut candy? Is it yummy?
Can you tell which one's the space food and which one is our regular Easter meal here?
Hey guys, what are y'all making?
Astronaut burgers.
I feel like I get to eat this delicious grilled food, and I get to eat a kind of brisket. It's space brisket and baked barbecue beans, so we'll see how that ends up being.
See this? Oh, it's coming apart.
Oh no!
Save the meat.
It's Monday, so we're done at Wednesday morning. We're really ready to be done. The weekend was hard.
I was not able to eat any of the food that was at the festival. There were some jalapeno corn dogs, and I'm like,
This one's so good.
what is life right now? I can't even.
And we have curry chicken, green beans and potatoes. The potatoes have been iffy, but these look better than some of the ones. Cream of mushroom soup.
Oh, a little bit of India, a little bit of Texas with this countryness. I'm so ready for this to be over.
Yeah, we're ready.
I need my social life back.
Yeah, no, I'm just.
Having milk today. Powdered milk. Ah!
We're nervous about yes.
I'm more nervous about the milk, I'm not gonna lie. But something that I noticed while we've been eating this food is you have to have it really hot.
On the space station, we put it in a kind of it's almost like an easy bake oven.
Okay.
Where you just, and that does make a really big difference.
So
I gotta admit, when I was making lunch this morning, I wasn't thinking this was gonna be on camera. Leftover rice, some turkey.
But it's home cooked.
It's definitely home cooked. Yeah, I was a big fan of the garlic paste.
Garlic paste.
That can fix anything.
Okay, question. Can you chew gum in space?
Yes.
Okay, because garlic, bad breath.
I wasn't trying to impress any of my crew members. We would use what we call food glue. something. We'll just make up something. Spray some olive oil in there to try to get everything to stick together a little bit. Or like I said, the garlic paste worked well for me. But when you get a few people with rice in their eye, then after that, you figure something out. You know, it's a lot easier in space because we don't have to load the syringe. Like if you were trying to measure out 250 milliliters of water or 100 milliliters of water, we literally just dial that number and then press the button for hot or cold water.
So talk to me about tacos in space. Tortillas, are they great to have up there? Yeah. Oh, sorry. It just floated on his plate.
Gosh, if we had salsa, we did have salsa sometimes. You can put that on there. The salsa will stick to the bread. You can use the salsa for other things to stick to the salsa.
I'm from San Antonio, and I love tacos. So I told everyone I would make a space taco. Yeah. So it's a little bit leaky, extra moist.
In space. It doesn't drip off the edges, it just makes a bubble.
Gotta do the taco tilt. Everybody knows. Good stuff. That's awesome. This was the Mexican scrambled eggs food lab. They know what they're doing. We have some scientists back there. So is there anything that you...
Woo, we did it! Way better than the LBJ toast.
Yeah.
Favorite meal, I actually really liked a lot of the breakfast food, and the shrimp cocktail was in fact very good.
Ooh, shrimp cocktail, but the scrambled eggs in a taco? Ugh, man, sorry. Done. And maybe if I had a machine to kind of heat everything up.
If I was sealed away from the outside world and I didn't have all those temptations, maybe.
Maybe if the food was floating around me, but I don't think I would otherwise.
We could do that.
If I were an astronaut.
So I was debating, this is the same debate I started with, nachos or a salad.
Get them both.
I'll get both. I should get both.
At this point,
Yeah.
I think we need to treat ourselves.
Oh, for sure.
But I can tell you, I really want some coffee.
Yeah.
Some nice
regular coffee.
Hot coffee.
Like
not
a latte.
powdered. I got to get some coffee.
And a soda.
This is not easy, y'all. I'm telling you.
Imagine living in a modern metropolis full of opportunities, endless sunshine, Hollywood celebrities, and fancy cars. That was the American dream. That was Los Angeles in the early 1940s. But in the morning of July 26, 1943, in the middle of World War II, the sun didn't rise over the city. A throat-burning noxious gas covered the sky. Entire city blocks faded away. A thick fog that made people's eyes sting and their noses run had taken hold of the city. They were under attack. Or so they thought at the time. But the attack didn't come from the outside. Massive wartime production facilities, a high increase in population, and the exhaust fumes of cars, combined with the geography of the valley, made the city a trap for air pollution. The day after the first event, city officials tried to control the damage by restricting emissions from power plants and industry. But while these efforts help reduce air pollution, smog episodes continue to occur. Scientists discovered that volatile compounds, like the gases produced due to evaporation of gasoline during the refining process, and nitrogen oxides generated during the combustion inside car engines, both reacted with sunlight, creating a highly toxic gas, ozone. And sunlight isn't precisely something Southern California lacks. But this wasn't a localized phenomenon. Other U.S. cities also experienced high ozone concentration levels. These cases made society aware of the importance of keeping track of emissions and lead politicians to implement policies to improve the quality of the air we all breathe.
Air quality is a serious global problem. More than 7 million people die per year due to the effects of air quality.
There's many economies around the world that are growing, and what the United States has seen is that your economy can still grow while your air pollution levels are decreasing, but it takes some effort to do that. The good news is that air pollution levels around the world are gradually decreasing.
In fact, air quality trends have improved in the last decade as a result of policies developed to reduce air pollution.
Back in the 1950s, Los Angeles had a really awful air quality problem.
So when the Clean Air Act began, it was a commitment to cleaning up the air. But the actual legislation and the differences took a long time to put into place. And so here in Asia, we're at the beginning of that process.
These nations that are still increasing in their standard of living and increasing in their pollution levels can learn from what's happened in the industrialized nations. We can have a more rapid decrease in pollution levels.
Now we know how to put together effective policies to control air quality.
Understanding that economic growth and industrial development bring air quality problems and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
QUICKTAKE is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem for the past decades.
Joint venture with NASA has provided us with many research opportunities.
The air in our planet does not know of national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
QUICKTAKE combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that the pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's three key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent for the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants. Nitrogen oxides and reactive hydrocarbons are most important in the formation of ozone.
Your car emits both NOx and hydrocarbons, sort of unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources. And so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules. And when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forests and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the fourth largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improve air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions. And so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the US. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally, the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab. Measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA, but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality, and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see, and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude, we see about a